Welcome to Structure for Architecture. In this video, I will discuss about the design of RCC water tank. Let us have a introduction of this topic. The most common types of overhead water tanks are number 1, the circular tank, number 2, the Inds type tank, number 3, the conical or the funnel shaped tank. Circular tanks with a horizontal or flat floor slab is economical for a smaller storage capacity of up to say 4 lakh liter, with diameter is in the range of 8 to 12 meter. The depth of the storage is generally between 3 to 4 meters. Now when water is filled in the circular tank, the hydrostatic water pressure tries to increase the diameter at any section. However, this increase in the diameter all along the height of the tank will depend upon the nature of the joint at the junction of the wall and the bottom slab. Now, if the joint is flexible, that is the sliding joint, the joint between the wall and the bottom slab, if that joint is flexible or sliding joint, it will be free to move up outward. So the hydrostatic pressure at the top is 0. So there will be no change in the diameter at the top, but the hydrostatic pressure at the joint at the bottom will be maximum, so resulting in the maximum increase in diameter there, and hence the maximum movement if the joint is flexible. So in this video I am discussing about the design of water tank, circular water tank, and the flexible base So, but in case of the base is rigid, the design differs. In that case, what happens? The side walls are designed for the circumferential hoop tension and the bending moment, since the walls are fixed to the floor slab at the junction. The design forces are determined using the coefficients recommended in IS 3370 part 4. IS 3370 part 4. The coefficients are expressed as a function of the non-dimensional parameter h square by dt, where h is the height of the water tank, d is the diameter of the tank, and t is the thickness of the tank wall. So please subscribe to my channel and look for more videos on the circular water tank with a rigid base. Currently in this video I will explain about the design of the circular RCC circular water tank with a flexible base. Let us read the problem. Design a circular water tank with a flexible base of capacity 4 into 10 to the power 5 liters. Depth of the water is 4 meter. Freeboard is 200 millimeter. And here we are using M20 concrete. And the permissible stress in the steel is given as 115 MPa. Now before starting of the problem, you should know some basic conversion, that is 1 liter is equal to 10 to the power minus 3 meter cube, and 1 meter is equal to 10 cube millimeter. So the capacity is given as 4 into 10 to the power 5 liter. So if we multiply it into 10 to the power minus 3, we will get 4 into 10 square, that is 400 meter cube. So first we will do this conversion. Depth of the water is capital H, that is equal to 4 meter. Freeboard is equal to 200 millimeters, so that is equal to 0.2 meter. And now we can start the problem solution. So step number 1, first we should find out the diameter of the circular tank. So effective depth of the water will be small h, will be total depth, height is depth of the water is 4 meter. So 4 minus freeboard, that is 0.2, that is 3.8 meter. Now if d is the inside diameter of the tank, volume is equal to, how we can find out the volume? Volume is equal to area multiplied by h. So volume is 4 into 10 square, and what is area? Area is pi by 4 into d square of a circular base. Area is pi by 4 into d square into what is height? Height is 3.8. So from this equation we can find out the capital D, that is the inside diameter of the tank, as 11.62 meter. So write the conclusion as provide a diameter of 11.7 meter. Now let us see step number 2. Unit weight of water is equal to 9,800 Newton per meter cube. or 10,000 Newton per meter cube or 10 kilonewton per meter cube. So these are the standard value you should remember. Now next is the maximum hoop tension. Maximum hoop tension can be found out by gamma h into d by 2. So hoop tension I am denoting here as capital H subscript T. So gamma value of water is 9800, capital H is equal to 4. D is the diameter. Just now we have taken the conclusion that it is 11.7 meter. So 11.7 by 2, that gives us 229.32 into 10 cube Newton per meter height. So area of the hoop steel that should be provided at the base, AST, we can find it out by the HT by sigma S, where sigma is S is the permissible shear, stress in the steel. So HT is 229.32 into 10 cube divided by 115. So that is 1994 millimeter square per meter. So area of the hoop steel at the base we have found out. Now let us take 20 millimeter diameter bar. So area of one bar is equal to pi by 4 into 20 square, that is 314 millimeter square. So spacing we can find it out 1000 into Fi by AST. This is the standard. These are all the standard steps for the RCC design. So 1000 into 314 and total AST was 1994. So if you put, it comes out to be 157 millimeter. So provide hoop of 20 millimeter diameter at the rate of, let us say, 150 millimeter center to center. Here you can take it as 160 also. Whatever it is, I have taken 150 millimeter cc at the base, but you specify it is at the base we are designing. So now AST provided is how much? AST provided we can find it out 1000 into Fi divided by S. So that comes out to be 2093 millimeter square. What is AST provided? That is how much finally we are providing. What is AST? Initially we have found out that is what is our requirement. Our requirement was 1994. Now currently we are providing 2093 millimeter square. Now step number 3, that we can find out the thickness by the empirical formula. So the formula given in the code, that is T is equal to 30H plus 50. Remember, H value you should put it in meter, and T value whatever you will get, that will be in millimeter. Don't try to match the units on the left hand side and the right hand side, because this is the empirical formula. So what is capital H? That was 4 meter. So 4 into 30, that is 120, plus 50, that is 170 millimeter. So that is the thickness. So let us provide a thickness of 170 millimeter throughout its height. Now step number 4. Now in the IS code it is specified that at the top of the tank minimum 0.3% reinforcement is provided, and spacing is also increased near the top. So AST is equal to 0.3%, means 0.3 divided by 100 multiplied by 1000 into 170. What is 170? 170 is the thickness and 1000 is per 1 meter length. So 1000 into 170, so 510 millimeter square. Now spacing, how we can find out? Same formula, 1000 into Fi by AST. We are providing 20 millimeter diameter bar. That decision we have taken in the step number 2. So 1000 into 314 divided by 510, it is equal to 600 millimeter. But here take a pause. In the code it is specified that the spacing cannot exceed 3 times the thickness of the tank. What is the thickness of the tank? 170. So 3 times of 170 is 510. So it cannot exceed that. So though we are getting it as 600 millimeter, but let us provide the spacing at the rate of 500 cc at the top. And what is the bar diameter we have taken? 20 millimeter diameter bar we have taken. We are not changing the diameter of the bar. Okay. Now see, as I have explained you earlier also, at the base, as it is a flexible base, at the base the diameter increases, and at the and also the hydrostatic pressure is the maximum. At the top it is less, so it will be economical for us and it will be judicious for us if we provide the let us provide the same number same diameter bar, but let us provide it economically by varying the spacing of the bar. Correct. For example, the total height of the water tank is 4 meter, that is given, at the top we have found out, we have given the bar spacing as the 500 cc. At bottom how much we have given? At the bottom base we have given as 150 millimeter cc, correct, center to center. Now let us say at the mid height means at 2 meter from the top, what will be the spacing? Because if we provide, though we can provide 170 millimeter center to center throughout it is, but it should not be economical, or we cannot provide 500 millimeter center to center throughout. So if to make it economical, if we vary the spacing of the bar, so it will be more economical design. So now let us design that part, spacing at the rate of 2 meter below the top. You follow the same step as mentioned in step number 2. What was the step number 2? That is, hoop tension is gamma h d by 2. Now the same step we are doing, gamma is 9800. What will be h? Now h will be 2 meter. In the step number 2, while we are designing for the base, h we have taken it as 4 meter. Now we are designing at a 2 meter height from the top. So it will be how much? 2. H will be 2. And D will be 11.7 by 2. So now this comes out to be 115 into 10 cube Newton per meter. So AST, for this is the similar as of the step number 2. If you have understood the step number 2, this is the similar step, only we are putting the value of capital H as 2 and then follow the same procedure. So AST comes out to be 1000 millimeter square per meter height. FI is 314 millimeter square as we are taking 20 millimeter diameter bar. So spacing here comes out to be 314 millimeter. Let us say, let us provide 300 millimeter center to center at the mid height. So now we have got all the data in a proper way. At the base we are providing 150 center to center. At top we are providing 500 center to center. At mid height we are providing 300 center to center. But the diameter of the bar is same, that is the 20 millimeter diameter bar. So this completes step number 4. Now let us design the step number 5, that is the vertical reinforcement. So vertical reinforcement are provided in the form of vertical bars. Number 1, at the rate of 0.3% of the concrete section up to 100 millimeter thickness, and at the rate of 0.2% for sections thicker than 100 millimeter and less than 450 millimeter. Here I am taking 0.28%. So AST is 0.28 by 100 into 1000 into 170. 170 is the thickness, so it is coming as 476 millimeter square. So vertical reinforcement, let us take it as 10 millimeter diameter bar. So one bar area is 78.5 millimeter square. So spacing comes out to be 165 millimeter. Now provide a 10 millimeter diameter bar at the rate of 160 center to center in the vertical direction. This is step number 5. Let us look at the last step, step number 6, that is the design of the tank floor. So here provide a minimum thickness of 150 millimeter. Nominal reinforcement of 0.3% in each direction is required. Let us see that how much it comes out to be. So AST minimum is equal to 0.3 divided by 100 into 1000 into 150, because here in the tank floor we are giving the thickness of 150. Okay, so it comes out to be 450 millimeter square in each direction. Now providing half the reinforcement near each face. So half the reinforcement means 450 by 2, 225 millimeter square. Now if you provide 8 millimeter diameter bar, area of one bar is equal to 50 millimeter square. So the spacing is it comes out to be 220 millimeter center to center. So provide 8 millimeter diameter bar at the rate of 200 cc, let us say, in both directions at the top and the bottom of the floor slab. And floor slab is resting on a 75 millimeter thick layer of lean concrete covered with a layer of tar felt. So next we will see about the design and the drawing details of the slab. So as you can see, that is this is the diagram, reinforcement detailing diagram of the water tank, circular water tank with a flexible base. 170 millimeter is the thickness and 4 meter is the height. So in the base floor slab, the thickness is given as 150 millimeter, as you can see over here, and the reinforcement details, as we have already found out that at the base it has been given 8 millimeter diameter bar at the rate of 200 cc in both ways. We have given a layer of M100 concrete also at the base and a layer of tar felt. This is about the floor slab. I am discussing about the bottom of the, from below, from the bottom to the top I am going, explaining the diagram. So, and after that there you can see that as I have discussed it earlier also, that we are giving the 20 millimeter diameter bar, but at the top it is 500 cc, then at the mid height it is 300 cc, and at the base it is 150 cc. So I have shown the 4 meter height into 4 section, 1 2 3 4, and like that way I have discussed. And in the vertical direction, as we have found out, we have given 10 millimeter diameter bar at the rate of 160 cc. So this is about the flexible base circular water tank design. Please look for the video for the circular water tank but with a rigid base. Thanks for watching. Please put on your comment in the comment box, or you can email me for any suggestion or any doubts. Thanks for watching.